Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to calculate torque. And what I'm going to do here is I'm going to take a look at this beam looking geometry. We're going to look at the following forces acting on it. We have this 100 Newton force acting up, this 30 Newton force acting down, this 50 Newton force acting up at the following points. I've got some geometry in here, a 2 meter distance, a 1 meter distance, a 1.5 meter distance. I've got 2 points labeled here, point A and point B, and I'm going to go through 2 examples of calculating torque, first about point A and then about point B. Now, one thing I'd like to point out, this video is just meant to demonstrate how torque is calculated. These are not going to be Newton's second law equations. This is not assumed to be a complete free body or anything like that. Just given these forces, how would we calculate the net torque about A from those 3 forces, and then again about B. And again, this is not intended to be a Newton's second law example. Now, a little reminder about torque. So first of all, this is the Greek letter tau. Lots of books use it to represent torque for whatever reason. I guess it kind of looks like a big T. Torque is force times distance, but they have to make a right angle. Whenever you do a torque calculation, it is absolutely imperative that whatever force you use and whatever distance you use, the force vector's line of action is perpendicular to the distance. So I'm going to go through here and go through this example. So first of all, let's talk about point A. I'm going to calculate the net torque about point A. And I'm going to start with this force right here and just work my way over to A. So this force acts all along this line. That's the line of action. The distance from A to where that force is applied is 4 meters. So the torque produced by the 600 Newton force about this point is going to be 600 newtons times 4 meters. And now I'm going to decide on a sign for this. Torque is a vector quantity. In a nice, easy two-dimensional problem like this, clockwise or counterclockwise is good enough. I'm going to go ahead and do counterclockwise positive. This force makes this object want to rotate counterclockwise about A, so that torque term is positive. All right, next, this guy. This 30 Newton force acts all along this line. That's its line of action. That line of action makes a right angle to the distance, just like the previous one did. So the force, 30 newtons, times the distance from A to where that force is applied, that's going to be 3 meters. Now for the plus or minus signs. This force makes this beam want to rotate clockwise. So I'm calling counterclockwise positive, so that's going to be a minus sign. And again, it's important to note this force makes it want to rotate clockwise about point A. All right, third force, this guy. Now you'll notice that the line of action goes right through A, so there is no distance. So I might put 50 newtons, but the perpendicular distance between this force vector and this line is 0. So this force vector does not produce any torque about point A. So that's it. And if we go ahead and take a look at this here, we can simplify this. This is going to be what, 2400 Newton meter positive minus 90 Newton meter. Looks like 2110 Newton meter positive, if I did that math right. I'm sorry, 2310. 2310. 2400 minus 90. All right, next, point B. So now we're going to sum torques about this point. Before I do, I'm going to rewrite this so it's legible. 2310 Newton meter, and that was positive, so in other words, counterclockwise. All right, summing torques now about point B. And again, that's, go ahead and put a little green dot there, right? So summing torques now about the green dot. This time I'll start left to right. So this 50 Newton force is going to apply a torque of 50 newtons. And again, the distance we want is this distance, which is 2 meters. That torque is clockwise, so I'm going to put a minus sign on it because I'm going to stick to my sign convention, counterclockwise positive. The 30 Newton force. Now the 30 newtons acts all along this line. The perpendicular distance is 1 meter, so we're going to have 30 newtons times 1 meter. And this also is producing clockwise torque about B. So that torque is going to be negative. Third force, 100 newtons. Perpendicular distance to B is 2 meters. And this is producing clockwise torque. I'm sorry, counterclockwise torque. This force is making this beam or this object want to rotate counterclockwise about B. Therefore, the torque term is positive. So here's an expression for the net torque about B. So this is going to be minus 100 Newton meter minus 30 Newton meter plus 200 Newton meter. If we add these up, this looks like it comes out to me to be positive 70 Newton meter. So the purpose of this video is just to give a very simple example of how torque is calculated about a point. Again, it's very important to realize that what the distances are going to be depends on what point on the object you're talking about. So typically when you're doing a torque calculation, you'll either be given a point or you will choose the point. Once you choose the point, then you look for the perpendicular distances to all of the force vectors, and then you decide on a direction to call positive. That will either be counterclockwise positive or clockwise positive, your choice. All right. I hope that this video helps give at least a sense for how to calculate torque. Have a great day.